All right, so my name is Owen Offman. I'm not Kent Gingerich, but I'm presenting on some of his research done within the fluid group. I'm an undergraduate research assistant at Liberty University, again under Dr. Strasser, and I'm also a sophomore mechanical engineering student. And then today I'll be presenting to you a validation of a coupled overset and smoothing mesh update method for fluid structure interaction. So first, boundary layer control is of paramount importance in FSI. And so it has many different applications within the aerodynamic and hydrodynamic fields, as you can see with planes, cars, boats, and submarines. Just for a closer look, especially in one example of an airfoil, we can see the differences between the flow across an airfoil with increased angle of attack. And as you can see, as that increases, turbulence occurs. And so this is not real data, but this is just a great visualization of that, and especially with that turbulent and flow reversal across our boundary layer. And so in orange, we have our boundary layer velocity profiles. And then the dark region is the area of flow reversal. And so flow reversals indicate of boundary layer separation. And so therefore, stopping that flow reversal is a good way to prevent separation and keep that boundary layer attached. And so once there is a significant boundary layer separation caused by that adverse gradient, the airfoil experiences stall, which also includes a significant drop in that lift. So one example in creation is the shark skin. This exhibits passive boundary layer control within what these are called are shark denticles. And so this control, passive boundary layer control, basically means that it controls that flow separation without using any other external energy. And so this automatically happens because of these 100 micron with shark denticles pictured here. And so these images were from a study from Santos and others. And then here's a more of a cross-sectional view of those shark denticles. And what happens is how they passively control a boundary layer is they become bristled as the shark continues to swim in the water. And so what happens is that that increased angle upward actually catches that pressure reversal and therefore makes it even more hydrodynamic. Then as those, and then some more work done by Santos. This color map represents the fraction of time the flow is reversed. And so at 50% is where you begin to see that flow separation, or a considerable amount even. And so that bristling angle is also very important. So here these graphs are aligned with the Reynolds number of 4.9E5. First with that flat plate, you can see a little bit of that flow separation. And then that bristling angle of 30 degrees actually increases that flow separation and pressure drag. But once you get to that 50-degree angle, it completely goes away almost. And then some more data with some higher Reynolds numbers. Still, that 50-degree angle is continuing to do its job up until around 8.1 E5. And so this evidence supports bristling up, of course, inhibits that flow separation. And so here I'm going to be going over some of our previous work. First, we've examined some large-scale characteristics of this flow separation, but it lacks fine-grained detail purposefully, as I'll elaborate on in a future slide. So we've decided to be using another method with direct numerical simulation, also known as downrights and Navier-Stokes, which is useful at low length scales. It resolves turbulent flow and it can visualize flow in a boundary layer. And it also gives us a broader quantity of data, but it is very computationally expensive. And so here we have 4 steps to take throughout the span of this research topic. First, we have our validation of the direct numerical simulation methods, and then creating a 3D moving and deforming mesh, and then our two-way coupled fluid structure interaction, and then finally model and mesh our real dentical geometry. And so right now we're in this section of our method, starting with 2 steps, rigid body motion, and then adding that body deformation. So what is dynamic mesh? Dynamic mesh is adjusted to capture the movement and or deformation of cell zone boundaries. And so as you can see here, this is the movement at which we will be simulating that shark denticle. Bit of a cheesy simulation, or a cheesy GIF here. And so yeah, these 3 methods are used to tackle mesh in ANSYS Fluent: smoothing, remeshing, and then dynamic layering. So first we're going to be looking at smoothing and remeshing. We have a combination of these two, and where what happens is smoothing first creates or that absorption of the motion of that boundary. And then, but there's no change in the number of nodes or connectivity. And so as you can see, those nodes continue to kind of compress, but not agglomerate yet until we get into remeshing. And that's closer in closer into our moving boundary there. It agglomerates badly skewed or sized cells and remeshes the agglomerated cells, but it's only available for tri or tetrahedral elements. And then our third method is dynamic layering. This adds or moves cell layer next to our moving boundary, but it's only available for extruded elements. It can only adapt to sort of rigid body motion, which is not perfectly realistic for our shark denticle simulation. But just some more about that. As you can see, this is an example of 2D dynamic layering with a rigid body. And this would be basically our denticle if it were to be rigid. And this can also be used for 3D simulations. And then here's just another 3D sort of visual here, beginning with our interior mesh. And this is our denticle. And then we have the rest of our interior mesh moving along with it in that 3-dimension scale. And then as well as our exterior interface. So because dynamic layering can't adapt to body flexure, it is not able to be used to adapt to a moving and deforming boundary. So in summary, the meshing update methods we've considered are: first, the coupling of smoothing and remeshing. This is very computationally expensive, especially in 3D. And it often creates very skewed cells right next to that moving boundary, as well as very often results in negative cell volumes, which kill the simulation for our arbitrary meshes. Then we have dynamic layering. Although it does not nearly have as many drawbacks as smoothing or remeshing, it's not very applicable with cases that involve deformation. So originally, the plan was to combine dynamic layering and smoothing to absorb the large-scale rotations and small-scale deformations of the denticle. However, using this method would not permit the coupling of ANSYS mechanical and fluent to perform our FSI. Therefore, we decided to pursue a different method, which is called overset meshing. So here are some work done by Nowak and others, exemplifying this overset meshing method. So here we have the arrow pointing to our background mesh, which is stationary, and then our component mesh, which can be static or moving. And so then the solution data is interpolated between those 2 meshes. So typically this method is applied to rigid bodies on that left diagram, but we can couple overset meshing with smoothing to allow for that deformation as well, inclusion. So smoothing, we can again use that for our component mesh. And so this maintains a high quality inflation layer next to the moving and deforming body, and it moves discretization error away from that component mesh. But to validate our methods, we're recreating another simulation done by Sway and others using the overset meshing and smoothing tools. As you can see here, they did a three-dimensional simulation of the dynamics of primary cilia in an oscillating flow. But what they used was the immersed boundary method, which we will not be recreating. But basically what happens is the ciliary basic rotations were modeled using an attached rotational spring at the bottom of that cilia, as you can see there. And so, but this immersed boundary method has difficulties in resolving thin boundary layers, and it overwrites the velocity values in each grid point to satisfy that boundary condition. And so here are our steps to create our FSI validation simulation. So first, we'll use a similar process as Nuak and others. We use ANSYS Fluent to solve the flow field, and then ANSYS Mechanical to solve for that cilia deformation. And then our method will be used to update that CFD mesh based on the deformations of the cilia calculated by Mechanical. This process will go as follows, using that overset method to capture rigid body motion, then combine it with smoothing to capture our deformation, and then couple Fluent and Mechanical to simulate our two-way FSI. So here's the basics of our domain setup and dimensioning. We have a purposely and obviously coarse number of elements here just to show a good visualization of it. Our periodic boundary conditions, a pressure gradient, which is specified across the boundary condition. We have a symmetry plane on the plus Z face, a no slip fall on the negative Z face, our fluid going from this direction in our X direction is air, and then some more of our dimensions. So here's just a bit of our procedure for our overset meshing. First, we cut our background or component in the cells that lie outside the domain. And then we minimize the overlap between the background and component mesh, where the smaller cells get a higher priority. So as you can see, there's much less just mess going on in this right diagram here as we've kind of cut out those overlapping cells. So moving the mesh causes the cells to change status from dead to solve and vice versa as you move. So this often caused simulation to diverge due to extreme velocity spikes. And so what we had to do was engage gas compressibility to cushion those velocity components. So as a first step, a UDF was defined or was used to define the motion of our cilia. Okay, thank you. And component mesh, as you can see here in our sinusoidal motion. So here are some of our results. As you can see, this flow direction, I'm very sorry that the motion is not perfectly in line, but shown below are our velocity contours normalized in our mesh motion animations for our rigid body for step 1. But this only involves the rigid body, of course, defined by our UDF. So while we can't validate anything yet, step 1 is a proof concept that shows that overset method with no smoothing can be used for the scenario. So to conclude, our overset coupled with smoothing is a promising method to update the mesh surrounding a 3D moving boundary. It maintains an inflation layer next to the moving and deforming boundary. And it does not require remeshing to absorb large boundary displacement. This is also available in Fluent natively, which makes it very easy. But this is the first step in creating that 3D two-way FSI model of that shark tentacle using our overset and smoothing coupling. And so thus far, as you can see, we've only used for that rigid body motion, and we did not produce orphan cells or diverging solutions. And so to conclude, our future work would be within step 2 to set the component mesh to utilize our diffusion-based smoothing, force the motion again, and then determine if we can converge on a solution throughout that cilia motion's range. And then step 3, couple the motion for our true FSI, validate the method by comparing the results from sway, and then step 4, apply to our beautiful shark tentacle. Thank you.
Sneak in a quick question. Yes, anyone?
So I enjoyed learning about sharks too. Is the idea, the emphasis behind this to just try to understand nature, or are we looking to implement some mechanical device to delay that separation?
Yeah, for sure. Yeah, this is definitely something that we can apply to within aerodynamics and hydrodynamics. But the problem then becomes, how can we manufacture that? Because what we've seen is 100 micron little denticle. Obviously, that's not realistic in creating. So we're just trying to use that concept and then later on apply it. But first, we of course need to validate our methods and how to simulate that.
Okay, thank you.
Thank you.